In this video I'm going to look at entropy, and you can see in brackets there a capital S, and that's because this symbol is used to represent entropy. So in the same way capital H is used for enthalpy. So you can see a picture on the whiteboard there, and it's a picture of the Department of Entropy, and you can see that the office is in a real mess, and that's because entropy is all about the amount of disorder in a substance or a system. So entropy is a measure of disorder. The more disordered something is, the higher its entropy. The more ordered it is, the lower its entropy. So if we have a look at the three substances on the board now, I've got carbon, graphite form, water liquid, and carbon dioxide gas. And in this column here, I've got their entropy, so there's that capital S again, and you can see the units of entropy are joules per Kelvin per mole. So what does that tell us about these three substances? Well, we can see the lowest entropy is graphite, very low number there, 5.7. So if you think about graphite structure, it's very ordered, there's a lot of regularity to it, so there's not much disorder to it, and so it has that low entropy. Carbon dioxide, on the other hand, is a gas. Gases have lots of randomness about them. They can go pretty much wherever they want, and so their amount of disorder is high, and therefore their entropy reflects that. And you can see there we've got an entropy of 214. So in very basic terms, solids have the lowest entropies, then liquids, because they've got a bit more chaos in their structures, and then gases have the highest entropies. So if we move on to a single substance now, so I'm going to look at water. How does the entropy of water change with temperature? We've got an entropy axis and a temperature axis, and notice it's in the Kelvin scale. So we've got 0 Kelvin, that's absolute zero, and at absolute zero the entropy of a substance would be 0. So this graph that I'm going to draw is going to start at the origin. So if we think about water in its ice form, so we've got low temperature. As you heat up water, or as you heat up ice I should say, the molecules gain kinetic energy, they vibrate that little bit more, still in solid form, but they do have more motion, and so therefore the chaos increases, and therefore their entropy will increase. So we'll try and make that straight line, yeah. Okay. And then something happens at a specific temperature whereby the water, the ice, will melt, and what that looks like on this graph would be a vertical increase. So what's happening there is the energy is being used to raise the entropy of the substance, so the actual temperature of the substance itself doesn't increase, but we get this increase in entropy. Once we've changed the state, so this is obviously going to be melting here. Once we've changed the state and we're in the liquid form, so this is ice, then the entropy can increase again with temperature, and we'll get another sort of straight line graph like that. So this is obviously water here. So as the water gets hotter, the motion increases, the chaos, randomness can increase, and then we hit another temperature whereby the entropy increases massively now because we're changing the water from liquid form into the gaseous state, and so we get this huge increase, and then it increases again like that. So this would be boiling, and then this is obviously steam, so gas, steam. So now we've looked at what entropy is and how entropy changes with temperature in a single substance like water. We're going to look at entropy change in chemical reactions now. So I've put on the board there a reaction that you may be familiar with. So this is the thermal decomposition of lithium carbonate. So if you heat lithium carbonate up, it will turn into lithium oxide and carbon dioxide. So the first type of question we'll look at is how do you work out the entropy change just purely based on the chemicals involved in the equation. So we're not doing any calculations at this point, we're just looking at the substances and sort of saying to ourselves, is the entropy going to increase? So that means it's getting more disordered, or is it going to decrease and get more ordered? So if you want to have a think about that one and pause the video, and then I'll run through the answer. So with questions like this, the way you've got to look are the state symbols. So if I just highlight the state symbols. So this reaction involves the conversion of a solid into a different solid and a gas. And the fact that you're producing a gas is telling us that the entropy is increasing because the CO2 has a very high degree of disorder. So we're starting out with a single solid substance which is quite ordered. So this will have a low entropy. This will still have a lowish entropy because it's a solid as well, but your CO2 has a big entropy, and so the entropy for this reaction would actually be increase. So due to that gas, we've got more disorder on the right hand side, therefore the entropy is increasing, and so we would say delta S is positive. So we'll do one more of these. Again, I'll just leave the equation with you to have a look at, and basically you decide whether the entropy is increasing or decreasing. You can see I've got the answer written up there. So how have I looked at this one? I've gone 3 moles of gas on the left hand side. That's going to have a very high degree of disorder, and those 3 moles of gas are turning into 3 moles of solid. So they're going to have quite low entropies because they're very ordered, and 2 moles of gas which are quite disordered, but the entropy will be greater on this side, the disorder will be greater on this side, and so the change in entropy, delta S, would be negative because you're going from a high entropy to a lower entropy. So we'll finish this video by looking at how to calculate values for delta S. So I've got the same equation as we used for the second example, but I've actually given you some entropy values now for all of the substances in the equation. So we've got the entropy value S in joules per Kelvin per mole, and you can see there 1 mole of SO2, 248, 1 mole of H2S would be 206, 1 mole of sulfur would be 32, and 1 mole of water, or steam, sorry, would be 189. So how do you calculate the change in entropy? Well, because entropy has the capital S involved, I use this acronym here. You might recognize that is the logo for a mini supermarket, the SPAR, and you can see that we've got S for entropy and S at the start of SPAR. So using entropies, the P stands for products, and if you imagine just that part of the A is a minus sign, and then we've got the R there, these are the reactants. And so to calculate the entropy change in a reaction, you take the sum of the entropies of the products, and from them you subtract the sum of the entropies of the reactants. So as an equation or a formula, that's how you would write that. So these sigma signs here stand for the sum of. And if you want to have a go at that yourselves now, pause the video and then I'll run through the answers. So hopefully you'll have got the same answer as me, minus 186 joules per Kelvin per mole. And the minus sign is telling us that the entropy is decreasing, so things are getting less disordered as the reaction goes forwards. And remember, when we looked at this equation at the start, just by inspection and just looking at the state symbols, that's what we said. We said it was getting more ordered or less disordered, and so the entropy change would be negative. But obviously you need these values to calculate the actual amount of change. I'll just finish with a very quick summary of what we covered in the video. Entropy has the symbol capital S. It's a measure of disorder. High disorder means high entropy. Solids have low entropies, gases have high entropies. Entropy increases with temperature. And just remember, at the phase change, you get that vertical section of the graph. Delta S is the sum of the entropies of the products minus the sum of the entropies of the reactants, or SPA. If delta S comes out as positive, that means the reaction gets more disordered, going left to right. If delta S comes out as negative, it's getting more ordered.